now we will have the next speaker, Meshgishe Chenis and Boakaz. Excuse me for my mistakes if they take place. Periodic solutions of the neutral delay model of single species population growth with iterative terms.
Good morning. Hello, everyone. First of all, I would like to thank the organizers of giving me the opportunity to participate at this conference. My name is Linda Mzrish. I am first year PhD student at 20 August 1955 Skikda University from Algeria. Today, I'm going to give a short presentation about the periodic solutions of neutral delay model of single species population growth with iterative terms. I divided my presentation into 5 main parts. In the beginning of it, I will present our problem. Next, I will convert this problem into an integral equation. And the third part, I will use Krones-Wilczynski's fixed point theorem for establishing the existence of positive periodic solutions of the considered problem. And the third part, I will show the existence and uniqueness of the solution. And finally, the presentation will end with a short conclusion. So let me start by presenting our model. Consider the following first order neutral differential equation with an iterative harvesting term. Equation 1, which can describe the dynamics of a single species population model, involves 2 types of delays. The first delay depends on time, while the second one depends on both the time and the population size, and which in turn leads to the appearance of the second iterate in our equation. Now, we will move on to the second part, where we will show where we convert this problem or our equation into an integral equation. In our study, we define the following Banach space of all T periodic continuous functions equate with the supermonar. Also, we consider the following subset is a closed convex and bounded of it. To simplify notations, we introduce the following constants. This is. In the current work, we need these assumptions, H1, H2, and H3. From the first lemma, we can convert our problem into the following integral equation, where the corner here is the Green's function given by expression 9. The corner G satisfies the following property, this. Let me turn now to the existence results. By virtue of lemma 1, we define an operator N as follows, where A and B are 2 operators given by expressions 10 and 11. From lemma 1, X is a solution of the neutral differential equation 1, if and only if X is a fixed point on the operator N. Also, by virtue of the Ascoli-Arzola theorem, we can show that this subset is a compact. So, for applying Krones-Wilczynski's fixed point theorem to prove the existence of at least one solution of our equation, it suffices to show that A is a continuous, B is a contraction, and this condition. Now, under these 2 conditions, 3 and 4, Lipschitz conditions, the operator A given by expression 10 is continuous. Indeed, for X and Y in this subset, and by taking into account the Lipschitz conditions 3 and 4, we arrive at this estimate, which shows that the operator A is a Lipschitz continuous and hence continuous. On the other hand, it's easy to show that the operator B is a contraction. And from lemma 4 and lemma 5, we can deduce the last conditions of Krones-Liskes fixed point theorem. Here, our first theorem. Let's throw in this subset. If conditions 5 to 7 hold, then equation 1 has at least one positive periodic solution. From lemmas 2 to 5, all conditions of Krones-Liskes fixed point theorem are satisfied. So the operator n has at least one fixed point in this subset. And consequently, our equation has at least one positive periodic solution. Now, we'll move on to the further part where we will show the existence and uniqueness results. Beside the assumptions of theorem 1, if this estimate satisfied or hold, then our equation or equation 1 has a unique solution in this subset. To prove, thanks to the last estimate, n is a contraction. This is. So the Banach contraction principle ensures that n admits a unique fixed point in this subset, which is the unique solution of equation 1. In conclusion, let me sum up the main step of our work. In the first step, we converted our problem into the integral equation, and we wrote the operator n as a sum of two operators, a and b. Afterwards, we proved that the operator a is continuous, the operator b also is a contraction, and this condition. We concluded that all conditions of Krones-Liskes fixed point theorem were satisfied, so our problem has at least one positive periodic solution. In addition, we apply in Banach contraction principle, and in additional condition, we prove the existence and uniqueness of a positive periodic solution. Here are our main references. Thank you so much for your attention.
Thank you very much. It's very interesting talk. And what questions do you have? Maybe I have one question. What is the motivation of solving these problems?
What motivation?
What motivation do you have to solve this problem?
I don't understand. Can you repeat, please?
What is the reason that you study this problem?
Okay. Our problem describes the population dynamics.
I mean that when you use this model, where you take it, where you can take this model, there are a lot of models of the size of population, and you use one of them, as I understood. And would you show, please, the first equation, the equation.
Okay.
Okay. Okay, thank you very much. I mean that your function h depends on t, x of t, and x.
This is the second iterate.
Second iterate. Okay. Okay, thank you very much.
Oh, no.
Thank you very much. I saw that, I mean that it's power, but it is not. I see the notion. Yes. Thank you. Thank you. Interesting. It's natural model in this case.
Yes.
Okay. Thank you very much.